chapter 11 in your text, we're really talking about, this is a really cool topic, we're talking about the STEM, thermo, which is dealing with what? What have you heard that starts with thermo? What do you think this is dealing with? Heat, energy, awesome. Like thermometer, like thermal underwear, things like that. So that thermo STEM is referring to heat and energy. So we're talking about the chemistry dealing with heat and energy and changes. And so what we're going to talk about is how is it that you can do these calculations to figure out how do they know how much energy is going to be released? How do you know if you're going to react to things that it's not going to explode in your face? Some reactions we had talked about earlier in the year will release energy. And if it releases energy, do you remember what we call those reactions? If they give off or lose energy, we call them exothermic. Awesome. If they gain energy, we call them endothermic. And so if it feels hot and there's a flame and things like that, then that's probably an exothermic reaction. Otherwise, if it's gaining and it's feeling cooler and it's making the surroundings cooler, it's gaining energy and taking energy from its surroundings, then that's going to be endothermic. So we're going to start off, and I want to show you this video. It's the spontaneous combustion of acetone peroxide, and it's used as an initiator. You don't always need to ignite a reaction. It can actually start itself. And what we say is we say that it's spontaneous if without you adding outside energy, a reaction starts. So watch this one. This is real. This is not a fake reaction. This is for real. I want to make sure that my volume's here. Oh, sorry.
Hey, Bob, can you give me a hand? Yeah, sure.
Okay, like that, with the spontaneous reaction, there are actually two things that determine whether a reaction will be spontaneous or not. One is its entropy, meaning how much what it has? Disorder. Awesome. How much disorder it has. And if something tends to become more disordered, then it ends up that it will be more of a spontaneous reaction. The other thing, the second part to having a spontaneous reaction, is whether or not a reaction or a process is exothermic. Meaning what again? What does exothermic mean?
Outputs energy.
Yep, it loses energy, it releases energy. And so those two things will determine spontaneity, but one of them being more like if you have a very exothermic reaction, it could be decreasing in entropy and still be spontaneous. So sometimes if one of them is really high, then you can still have a spontaneous reaction. So again, the idea of what a spontaneous reaction is, so just the word spontaneous, it's simply that a reaction will proceed in the direction written without adding outside energy. So reaction proceeds with no outside energy added. It just takes place. You don't have to add anything on the outside, and the reaction just takes place. Why is heat given off when you burn fuel to warm your house or cook your food? Why is it given off when you burn a candle? Where does the heat come from? How did the heat get into the fuel in the first place? So that's what thermochemistry is. So hopefully you'll have a better idea after we work on this unit as to why it is that you can burn something and then it gives off a certain amount of energy. So thermochemistry is concerned with heat changes that occur during reactions. Every chemical reaction is associated with these energy changes. For example, when you buy gasoline, you're purchasing the stored potential energy that it contains. So what do you have to do in order to use that energy? You burn it. Perfect. You burn it, and then there goes your car. Okay? So this energy may be used to do, it's a physics word, it starts with a W. It may work. Nice. It may be used to do work, to propel the car. A mixture of gasoline and air is ignited in the engine, and then that ends up releasing the energy. Similarly, you eat a piece of chocolate, and that can provide your body with energy as it's burned up with oxygen in the cells of your body. What's that called? Starts with an R. AP Bio, human bio people. That's called respiration. Nice. That's called respiration. And the equation is you have your sugars plus your oxygen, that's what it's burning in. And what two things do you get? And it's a CH reacting O2 with CH or CHO always produces? CO and HO, CO2 and what's HO? H2O. What else, AP Bio / Human Bio people, what else is made then that we would use then as energy? What is that called? Anybody remember? It's 3 letters. ATP. Awesome. Awesome. And it's like 38 ATPs, like in the glycolysis cycle, they have the different cycles. Okay. So the branch of chemistry that deals with energy changes associated with chemical change is called what? What is this whole thing called? Thermochemistry. Yay. Thermochemistry. Oops, my pen's going out. The origins of this term should be obvious. Thermo is a prefix that's associated with the concept of what? Heat. Very good. And chemistry is just the study of matter. Hey, it's what matters. Just kidding. Okay. And the changes it undergoes. First law of thermo. So we're only doing the first law of thermo. There are 3 laws of thermodynamics. One actually deals with entropy. In the third law, it deals with entropy and says that if you're at 0 Kelvin, entropy is 0. Everything is, there's no disorder whatsoever, because what happens when you're at 0 Kelvin?
Particle movement.
Yeah, everything would come to a complete stop. So that's the third law. The first law is dealing with just energy of the universe is constant. Awesome. Meaning what? There's no, can't be neither created nor destroyed. So that whole idea of created nor destroyed, whatever your energy is for your reactants, that's the energy for your products. It's just a rearrangement, okay, of everything. Bless you. So let's break up the definition. So we have energy first. Energy, so we're going to define what energy and universe, we obviously know what constant means. Energy is a difficult term to define in a meaningful way. Most textbooks will say it's the capacity to do work or to produce heat. That's how they define it in books. What do you think of when you hear the word energy? So try not to look down for a second. When I say energy, what first picture comes to mind? Whatever it is that you're thinking. I say energy, what comes to mind?
Lightning bolt.
Lightning bolt.
Sun.
A gun? A what? What did you say?
Fire.
Sun.
Oh, the sun. The sun. Thank you. I was like, it could be. What is it?
People moving around.
People moving around. Awesome. Who else?
What I'm
Energy.
lacking.
Fire.
Fire?
I said what I'm lacking.
What you're lacking. Okay. All right. So, and there could be a whole bunch of other pictures that come in your mind. So you probably think of maybe heat, light, like when you were saying the sun. That could be something where you're thinking of the heat and the light. Electricity. Some of you may have thought of electricity and a light bulb. Sound. Things in motion. So, or lack of, right? So, for example, when oil is burned, you see light, and then you sense an increase in temperature. If the oil explodes, you're going to hear a sound. And then you can either see or feel objects in the vicinity that are exploding, moving, or maybe they're breaking. You might even see things in the area that are melting. If the oil's burned at a generating station, then you can actually get that to create an electrical current and use that for electricity. So it turns the turbines or the generator. Try thinking of the capacity to do work or produce heat as being somehow related to motion, sound, light, for our purposes in terms of heat. Okay? For our purposes, we're going to think of it in terms of heat. So the second word was talking about what this universe is. Okay? We didn't talk about the universe. A system is simply anything that you focus your attention on. We're going to call that the system. In chemistry, it's usually the substance or whatever mixture of substances that you have that are undergoing some type of change, whether it's nuclear or physical change or a thermal change. The surroundings are just everything what? Yeah, around it. Perfect. It's just everything around the system. And it's everything that interacts with the system. That's what you're just going to call the surroundings. And the universe is both the system and its surroundings. That's what you're going to call the universe. It's both of them together. Okay? So if you mix something into water, then water is going to be affected by it. So that would be part of your system and the surroundings, including the air that's around it. Okay? Then that would be your entire universe that you're looking at. Endothermic versus exothermic. So we talked about this before. We can restate the definitions of exo and endo in terms of these systems and surroundings. So exo is one where heat is flowing from where? The system out toward the surroundings. So energy is being Released, or another word is, starts with an L?
Create.
Lost. Very good. An endothermic is one where heat is flowing from the surroundings into it. Nice. So we say energy is?
Gain.
Yep. Absorbed slash gained. Very good. Okay. I have two substances. One, we're going to create a hot pack, and the other one, we're going to create a really simple cold pack real fast, okay? Now, it takes a lot more to be able to get one that's going to last longer, too. So I'm going to pass this around the room. What I have is, I have two different chemicals, both safe chemicals. So we've got calcium chloride. Anybody know, as safe as chemicals can get here, anybody know where you have used calcium chloride before? Maybe your parents have used calcium chloride, or maybe, what's that?
Fertilizer?
We'll come back to that one. Calcium chloride, like magnesium chloride, like sodium chloride, is used in rock salt. Awesome. That's used in rock salt. We will be making ice cream. And so calcium chloride, the rock salt, you can actually get the temperature to decrease. So we'll talk about that also. It's a really fun thing to do. The other one that we're going to use is ammonium nitrate, which that one is?
Fertilizer.
In fertilizer. Perfect. Okay. And we'll get the formulas down in just a second here. But all I'm going to do is put them in Ziploc bags separately. I am not mixing these together, okay? I'm going to put this one in water. I'm going to put this one in water. One of them's a hot pack. The other one's a cold pack. I'm doing exactly the same thing to both of them. It's not really a chemical reaction. I'm just dissolving them, meaning they're going to be, what do you call it when you dissolve something in water? Aqueous. Awesome. Nice. So we would call that aqueous or aqueous. And we're just going to dissolve it in water. And people have a misconception, okay? One misconception is, and I want to make sure that I talk about this, is you think about the whole bio thing, okay? And typically what people will say is, by breaking apart sugar molecules, we have done what? Created what?
Energy.
Energy, okay? But it's not actually a true statement. Well, it's partially true, okay? If you're specific about the sugars. Breaking bonds never releases energy. Think about it. What's holding a molecule together? Like a sugar molecule, like a salt molecule, or salt formula unit. What's holding them together? What do we call those? We did this in a couple units ago. IMFs. Awesome. So we have forces, electrostatic forces, or IMFs. There are three kinds. There's the strongest of them, which is the hydrogen bond. Then there's dipole-dipole. The weakest of them is London forces. Okay? So you've got these forces that are holding them together. To break any bond requires energy. It always requires energy. And if it requires energy, that's an endothermic process, meaning it absorbs energy. So why is it that breaking apart sugar molecules actually gives off energy and gives off all of this ATP? Why is it? Because it's not just the breaking of the molecules. What is it?
The releasing of energy.
So what causes the release of energy? You need to look at the full what? You can't just look at breaking sugar molecules apart. What do you have to look at?
Whole system.
The full system, or the full, what do we call it in chemistry? We call it a process, or a, starts with an R.
Reaction.
Reaction. Thank you. You have to look at the full reaction. And it's not just sugar molecules breaking apart. What did we say respiration is? What's happening to those sugar molecules? You're reacting them with what?
Oxygen.
Oxygen gas. Okay? You're reacting them with oxygen. And the idea is very simple if you've ever played with Legos before. Okay? My kids love Legos. So let's say you've made this building. Okay? But now you want to make some like spacecraft. All right? Then what you need to do is you need to take these all apart. Every single Lego piece, you need to pull them all apart. And then what are you going to do to them?
Put them back together.
Put them back together again. You check to see how much energy it took to pull them all apart and how much energy it takes to put them back together again. If this one is more than this one, you would actually subtract the two, and then you would check to see what's my net, okay? And if you end up with more energy than what you started with, then it's exothermic. You have a release of energy. If you end up with less energy in your products than you had with your reactants, then that would be considered an endothermic reaction. Okay, so it's almost like you have to pull them apart in your reactants. You're pulling everything apart, and then you're going to rearrange them in your products and put them all back together again. And it all is an energy in. It always requires energy to break the bonds, and then to put it back together again releases energy. But sometimes it can go either way. Sometimes it's exo and sometimes it's endo, which is why I want to show you how I'm going to do the same thing to both of these. Just put them in water, and you'll see that one of them will be exothermic, the other one will be endothermic. And in the dissolving process, it's called the solvation process. It's actually 3 steps. Water has to go in, and it has to separate them from each other. It has to separate the molecules from each other, okay? And so once it separates them from each other, then it has to surround the molecules, and depending on the entire process, sometimes it's exo and sometimes it's endo when you add them all up, okay? So I'm going to have you watch this video while I set this up. And there's someone, I don't know if he's like another student from, he's not from here. And I'm just going to have you watch this. It's just 48 seconds while I set this up too about hand warmers.
The other day I went skiing and I brought with me a set of these, hand warmers. As it turns out, there's an incredible amount of chemistry contained in this tiny little mesh bag.
To understand the chemistry here, let's first take a look at the ingredients. Inside every hot hands hand warmer, there is iron powder, water, salt, carbon in the form of activated charcoal, and vermiculite. On the outside of the package is oxygen in air. Iron meets with oxygen from the outside along with salt as a catalyst and produces iron oxide, Fe2O3. This is an exothermic chemical reaction, meaning that heat energy is released in the making of the ionic bond. The vermiculite helps keep the heat contained and hot within the reaction. And just like the coals on a barbecue, the charcoal helps dissipate the heat to the entire hand warmer. As long as iron keeps reacting and the carbon stays warm, the hand warmer will stay hot. After a while, the reaction stops and the carbon cools down, making the hand warmer irreversibly return to its initial state. So the next time you hit the slopes or use hand warmers for anything, you can thank iron oxide, charcoal, and chemistry for keeping you toasty warm.
Yay, toasty warm. Okay. All right. So, let's go back to this. All right. So we've got 2 things. Let me just bring the water over here so that you can see. Okay. So I've got 2 of these. I'm going to start off with the calcium chloride. Okay. And all I'm going to do is I'm going to add water to it. So it's room temperature water. Okay. So I'm just going to add a tiny bit of water to this, and then I'll pass this bag around. Just try to just give it a feel, and then you can pass it along to the next person. That's okay. So let me start this one off on this side. Tell me what you think of how it feels. How does that feel to you? Warm? Okay, and you can pass that along. So just give it a little mix. Try not to hold it over your papers just in case it drips a little bit. And we can rinse hands if you get any on. But, okay, this other one, same thing. I'm going to do the same thing to this. This is the ammonium nitrate. What do you think of this one? In comparison, very cold. Okay, so the ammonium nitrate gets really cold. Again, I did the same thing to both of them. One of them ends up being hot, and the other one ends up being cold. So the calcium chloride is the one that was hot. The formula for calcium chloride is what? Calcium is just Ca, right? Anybody remember the charge of calcium? Plus 2. Nice. And chloride is Cl. Well, it'll be Cl2 because chloride's -1, so it's CaCl2. All we did was dissolve it in water. Okay? So it's just a process of just dissolving it in water. And what did we find when we dissolved it in water is this is the one that got hot, meaning that the temperature increased. Okay, so that's the one that felt hot. That would be the hot pack one. All right, the temperature increased, and if the temperature increased, what does that mean that the molecules did? What did the process do? Did it release energy or did it absorb energy if it now feels hot, if it feels hotter than before? It released. Awesome. So write this down. It released energy. Okay, it released energy. And if it released energy, do we call that exothermic or endothermic? Exo. Awesome. That makes it an exothermic reaction. And now let's see if you remember this. There's a sign that we can associate with it. Okay? Exo, remember, means losing, releasing, giving off. I'm going to repeat, losing. What sign do you think the delta H is if it's losing energy? Losing would probably be negative. Awesome. Okay? So an exothermic reaction is going to be negative. If the temperature increases, then that means that the reaction is losing energy. But I want you to keep in mind that something else is gaining it. Because by the first law of thermodynamics, energy is neither created nor destroyed. So if this is losing the energy, who's right around to be gaining it?
The area?
The water. Perfect. The water around it, and that's why if you put a thermometer in there, if it's getting warmer, you would expect the temperature to be higher. Okay? The cold pack. The cold pack is ammonium nitrate. Who remembers what ammonium is? NH4 with a plus charge. And what's nitrate? NO3. You can just leave it in the sink back there if everybody's trying to touch this. Okay. So this same thing, we're just dissolving it in water. Dissolved in water. And in this case, we saw that the temperature decreased. Okay, so that one got cold. So did this one release energy or absorb energy? Absorbed energy. Guess where it absorbed the energy from?
The surroundings.
The surroundings, which would be the water or you if you're touching it or the air around it. Okay, so it's going to absorb energy from anywhere from there. So we would call this one not exo, but
Endo.
endo. Awesome. And in this case, delta H would be positive. Awesome. Okay, measuring energy. So how is it done? You can use what is called calorimetry. So it's a process of measuring heat changes. A calorimeter is a device that measures quantities of heat. What stem are you seeing in this word?
Calorie.
Calorie. Awesome. So you can see the calorie in there. Calorimetry is based on the idea that energy lost must equal the energy gained. Awesome. By the surroundings. So we're just repeating what we had said before. And vice versa. In other words, it's based on your first law of thermo. Heat changes for most processes can be determined by using one or more types of calorimeters. There is what is called a simple calorimeter, and that one's constant pressure. Or you can use what is called a bomb calorimeter. And we'll talk more about this on Thursday, the bomb calorimeter. It's not really a bomb going off. It's like an isolated container. I'll show you what that looks like. So let's just do coffee cup right now. So the simple calorimeter consists of, typically, and I'm going to show you a fancier simple calorimeter. Okay. So what I have here is, this could really just be a styrofoam cup, okay, with a styrofoam cup, a second cup covering it, like nestled in it. So I'm just going to take this all apart so you can see what this is. Styrofoam cup, that's called the insulation, okay? That's our insulation. If you're reacting acids and bases, what would an acid do to the styrofoam?
Dissolve it.
It would eat away at it, and then it reacts with it, and then you don't have any more styrofoam in there. So that was useless. So what we do is we use these for acid-base reactions to check to see how much energy is released or absorbed when you react the acids and the bases. So I'm going to put, then we have this metal container, just so that we can put our reactants, our substances inside of there. Okay. Then this goes inside of this container. And then this is just a cover just to make sure that if you have like acids or whatever, that it's not going to eat away at the styrofoam. The rest of it is just this cover here, because we don't want to lose energy outside, so we cover it up. Okay, it's not the best insulation. Typically, styrofoam, again, being around it would be better than using this, but it works. There's an opening right there so that you can add your substances in. Once it's closed, you can add your substances in. And then this here is to do what? What do you think?
Mix.
Stir it. Perfect, because you want to make sure that it's even, going all around. And then there's one more hole, and that's where your thermometer goes. Okay? And so you would just measure the change in what? In temperature. But there are things that matter. For example, what substances is inside of there matters as far as your temperature change. The other thing is the amount of mass that's inside of there matters. I'm going to exaggerate this. You have a friend you send out into the middle of Orchard Lake on a little boat, okay? Tiny little boat. And you give them a pot of boiling water, okay? And they go out into the middle of the lake and you give them a thermometer, okay? And then you're with them on a cell phone, all right? Your other buddy is right on land, okay? And they have a pot of water, and then they have another kind of big little, I don't know, tiny little thing, a little bucket type of thing, okay? And you count to 3 and you go, are you ready? 1, 2, 3. Dump the water in, and they're waiting, and they're going to check the temperature. What's going to happen to the person that's in the lake, that's sitting in the middle of the lake? Will they read any difference on their thermometer?
No.
No. Why won't they be seeing any difference? They dumped an entire pot of hot boiling water into the middle of the lake.
Because
why aren't they seeing any temperature change?
There's so much matter to heat up.
Yeah. The lake is too big. Okay? It's really going to absorb all of that change, and you're not going to see any difference. The person that added the boiling water into the bucket, will they see a change?
Yes.
Yes, probably, okay? But I'm going to tell you something about water. We're going to talk about what is called the heat capacity, and I'll give you a chart of different heat capacities. Water's capacity, it actually absorbs a lot of the energy change, a lot of the temperature change that you have applied to it, and so it just has the capability of doing that. And so water doesn't really change very much. We'll talk more about it on Thursday. Whereas other substances change much more quickly, and you'll see a bigger change in between, and that's what you get a value called the specific heat or the heat capacity. Water's is up around 4. I'll give you the exact numbers, 4.184. We'll talk about that later. Whereas most substances are under a value of 1. Okay, so we'll go through those charts later on. So what is a simple calorimeter? It consists of, what do we say has to be on the inside? Some
Cup.
insulation. Awesome. So some type of an insulated container. Some insulated container. The second thing that goes in there is a blank. What else do we need in order to measure the temp change? A thermometer. Very good. A thermometer. And you also need a known amount of, what do we call these? It can be any different type of chemical. What's a general term for all of them? Substances. Okay, and a known amount of substance that's in there. It's used to measure heat changes associated with cooling, phase changes, solution formation, and then different types of reactions. Together, the contents and the components of the calorimeter are an insulated system. So energy is not supposed to be entering or leaving. We know that we don't have a perfect system, so like even when you do the lab, we'll end up doing a lab on this. It's not perfect, okay, so you'll end up writing that in your error. The experimenter places the reactants into the container and simply records the change in the substance's what?
Temperature.
Temperature. Awesome. If there's a rise in the temperature, circle the word rise. If there's a rise in the temperature, that means the reaction released energy, so we would call that exo. Awesome. That one's exothermic. Okay? And remember, if it's exo, your delta H is positive or negative? It lost it. Negative. Very good. If the temperature decreases, so I want you to circle the word decreases, it indicates the reaction absorbed, so I'm going to underline the word absorbed energy, and the reaction is now endo. And so we would say delta H is positive. Awesome. Heat flow is calculated using the relationship, I'm going to call this the MCAT equation. Everybody say MCAT. MCAT. We're just going to label these. We'll do one problem, and then we're going to take a break. Okay? So they're really easy to use. We're going to do MCAT equals MCAT later, but we're just going to use this MCAT equation first. Okay? So this Q, or this delta H, is the heat change, right? So what units would we measure the heat change in? Well, it's energy. So what do you know that we've measured energy in before?
Kelvin.
Joules or
Kelvin.
calories. Awesome. So you can either use, usually we'll use kilojoules per mole. Okay, actually I'm just going to leave it as kilojoules, because I'll tell you about the mole part later on. Okay, so just leave it as kilojoules. It can also be joules, calories, or kilocalories. Okay, it can be any one of those. M would be what? What do you think M is in this case? We talked about the lake idea. M is probably the mass. Awesome. And the mass you're going to measure in grams. Okay, that's usually done in grams. C. C is what I was referring to. Anybody want to guess? It's a constant, but what did I didn't, someone may have said it. It's called there are two words for it. The heat something that starts with the C. The heat. It's called I'm not sure if someone's saying it. Someone might be saying it. Either the heat capacity or it's called the specific heat. The specific heat or the heat capacity. This is a constant. There's a chart, and every substance has a specific heat or a heat capacity. So usually we use water. I want you to box this in because we're going to use it on the next page. All right. This will always be given to you. Waters will always be given to you because we use water so often in solutions. What is delta T?
Change in temperature.
Change in temp. Awesome. Change in temp, and I want you to put a star. It's the absolute value. Okay? So it doesn't really matter. Typically you do final minus initial, but we're going to do absolute value, so no sign, okay, for your temperature change. Two important things before we do one calculation here. One is your MC and your delta T, when you use this, have to all be for the same substance. So if that's water, that has to be water, and your temperature change has to be water. If that's gold, a piece of gold, then your mass has to be of the gold, and your temperature change has to be of the gold. So you have to make sure that they're all the same. 2, the sign of delta H depends on whether energy was gained or lost, and you're going to assign the sign, if necessary, yourself. If energy is lost, who remembers delta H is? Negative. If energy is gained, delta H is? Positive. Awesome. So typically, if your temperature goes up, then the reaction is releasing heat. So in that case, it would be negative. Okay? So if it gives off energy, then it's releasing or losing, then it's negative. Okay, let's just try one question here. Consider a reaction which occurs in 200 grams of water. What do you think this let's just write, we did this in the last unit. So what do you think this 200 grams would be representing in delta H equals MC delta T? Mass. Awesome. So that's going to be our M. With an initial temperature of 25 degrees Celsius, is that your delta T?
No, Kelvin.
Why not? It's not a change. Awesome. If they said the change in temperature is, then you'd be good. But they're saying the initial temperature is that. So we're okay right now. The reaction is allowed to proceed in the calorimeter. As a result of the reaction, the temperature changes to 31 degrees Celsius. Not it changed by 31 degrees. It changed to 31 degrees. So in that case, we can figure out our delta T. Calculate the energy change in kilojoules per mole. So what are we looking for if we're being asked for the energy change? Which one of these are we looking for? Delta H. Awesome. Okay. So delta H is equal to, we said the mass is the 200 grams of water. So you want to make sure everything's going to be for water. The specific heat of water is on the page before. Now, we have 3 choices. We could either use calories, kilocalories, joules, or kilojoules. Which one do you think you want to use? Kilojoules. Why? Because that's what they want your answer to be in. So that means we're going to use the first one, the second one, or the third value that's given to us? The third. Awesome. There's our kilojoules. So similar to when we were doing R in the last unit when we were doing gas laws, and you had to pick out which R you were going to use based on the pressure. Now we're picking out which one of the C's. They're all equal to each other, but just depending on the units. Okay, so let's use the C, the 0.004184 kilojoules per gram degree Celsius, and you'll always be given the constant. You don't have to memorize it. Then the delta T. So our temperature change is, we said from 25 to 31, which means our temperature change is what? 6 degrees, 6.0 degrees Celsius. Because it's 25.0 and 31.0, when you subtract, you also want to stop at the 10th place. Okay? Remember, adding and subtracting is different from multiplying and dividing. Okay? So now you're just going to, oh, by the way, you would just multiply this, right, to get your answer? Our units cancel out, the degrees Celsius with the degrees Celsius, the grams with the grams. I had someone ask in second hour, don't you have to change that into Kelvin? First of all, this is in Celsius, so I want to make sure I can cancel my units out. Okay, but I'm going to tell you that it doesn't matter because you'll still get 6 degrees. Why?
This is the absolute value.
And not only that it's the absolute value, why is it the same difference? Perfect. You're adding 273 to both of them, so your difference is still going to be the same. So whether you use Kelvin or degrees Celsius, sometimes they'll give you your constant in Kelvin. It doesn't really matter. Okay? That's it. So go ahead and multiply this, and please tell me what you get.
5.0208.
5.0. Okay, perfect. So and let's do 2 sig figs because that's 3, 4, and 2. So 5.0. What units would this be in then? Kilojoules. Awesome. Sign. Did it rise in temperature or did it drop in temperature?
Rose.
How do you know? 25 to 31. That means our temperature went up. And if your temperature goes up, then that means that it was an exothermic process, so releasing energy. So what would your sign be?
Minus.
Negative. Awesome. And this just explains that. It says because the temperature of the water increased, the reaction must have released energy, just like we said. So what would you call that type of reaction then? Exo. Awesome. So delta H then would be negative. If the reaction released energy to the water, then the water must have done what? Absorbed it. Awesome. The water absorbed the energy. So I want you to understand that one of them's negative, then the other one must be positive. Okay? And then this just shows it in joules as negative 5.0 times 10 to the third. Okay, we're going to take a break and then we'll come back. Alright, so we're back. So the last thing we're going to do is we're going to do what is called an MCAT equals MCAT problem. Okay? So I'll explain this in just a second here. So one of the major uses of calorimetry is to measure what are called the specific heats of different substances. So the question is, how do they get, and I'll show you this chart on Thursday, how do they come up with this big chart that has all these specific heats? And what they did was, they basically used water as the reference. We talked about how many joules per gram degree Celsius or kilojoules or calories per gram degree Celsius. And water's ends up being 1 calorie per gram degree Celsius. And by definition, what that means is 1 calorie is defined as the amount of energy that it takes to be able to raise how much water? Anybody know?
1 gram.
1 gram of water by how much?
1 degree Celsius.
1 degree Celsius. Awesome. And that's the definition of the calorie. So it's 1 calorie per gram degree Celsius for water. Okay, so that works for water. So what the scientists did was they figured out the specific heats of other things. And now you're thinking, well, why does this matter to me? What does that do for me? So I'll tell you that in things outside of chemistry, like in architecture, engineers, where if you're you're going to build something, it's a building, it's a home, and you want to know what type of substance you should use on the outside of your home. Well, depending on where you are, maybe for your roofing, maybe for the siding and things like that, different substances work differently as far as how much energy they can absorb. And so maybe you want it to be absorbing a lot of energy and taking in a lot of those energy changes. Maybe you don't. So those materials will make a difference. So it says chemists use specific heats in their study of the structure and attractive forces in materials. Specific heats, which is given the symbol C. Sometimes it's given the symbol S with the little p. We're going to use the C. Are useful for engineers in planning structures or processes. The use of calorimetry is based upon the law of conservation of energy. That energy is neither created nor destroyed. Perfect. But it can be transformed from one form into another. In this application, hot metal is added to cold water in a calorimeter. I'm going to show you this in just a second here. The cold water gains the heat lost by the metal as they come to the same final temperature. If you measure the temperature changes, you can calculate the heat gained by the water, and thus the heat lost by the metal. And finally, you can calculate the specific heat of the metal. And the idea is that whatever was gained by the water must be
Lost by the metal.
Lost by the metal, meaning the two values are equal. There you go. Now we've come up with an equation for it. Okay? So what this turns into is MCAT equals MCAT. And it doesn't matter if you put the metal on this side and the water on the other side, as long as your two substances are separate. Because I had said before that these three need to be for water, and these three need to be for the metal, or the other way around. So let's try a question. I'm going to show you what this looks like. So what I have here is, I'm going to say that I have boiling water. Okay? So it's at 95 degrees Celsius, okay? Almost boiling. A metal with a mass of 125 grams. Now this is 200 grams, okay? But let's just imagine that this were a 125 gram piece of metal, okay? And it's at a temperature of 95 degrees Celsius, meaning that I took this piece of metal and I left it inside of this near boiling water. Okay, get these out of the way here so you can see. Okay, so if the water is 95 degrees Celsius, what's going to happen to this piece of metal? It's eventually going to do what? Going to become what? 95 degrees. Okay, and it doesn't take long for metals to heat up to that temperature. So now this metal is 95 degrees. Then you take it and you're going to drop it into a coffee cup calorimeter. And the coffee cup calorimeter has 250 grams or 250 milliliters of water in it at 23 degrees Celsius, which is basically about room temp. So I look at this and I've weighted and I read this and the thermometer says that it's 23 degrees Celsius. I'm going to take this off because it won't fit inside of there. And what I'm going to do is I'm going to take my hot metal, okay, it's not really hot, but I'm going to pretend, okay. I'm going to take it that's at 95 degrees, and I'm going to drop it into my calorimeter, and I'm going to cap it and check to see, and you would stir it, okay? And check to see how the temperature of the water changes. Do you think the temperature of the water is going to rise or drop when I add the hot metal into here?
Rise.
Rise. By a lot or by a little bit? Okay. Not by a lot. You're going to see that water's temperature change is only slight. It might be 1 degree or 2 degrees, if that. Water has a really high heat capacity, meaning it will absorb the heat changes that you give it. Okay? Most substances will change very rapidly and change at very high temperature. Water doesn't. And that's what's kind of nice about water, and that's why a lot of times we like to use water in these reactions to check to see that. But it does actually stay pretty constant. Okay? So let's do this calculation. It says the water and the metal finally reach a temperature. So inside of our calorimeter, we want the biggest temperature change. And we find out that it started at 23, but then the water and the metal reach a final temperature of 35. Okay? So the question is, what's the specific heat of the metal? So let's write our equation first, and we'll do it the same way that this is set. So we're going to do our metal change is equal to the change of the water. So we're going to write MC delta T equals MC delta T. Okay. Do we know the mass of the metal? What does it say in the problem? 125 grams. Awesome. The specific heat of the metal is what we're looking for. So that's our C of the metal. Again, it's on the metal side. Can we figure out the temperature change of the metal? This is the hardest part of this. What did the metal start as? It was in the hot beaker. What did it start as?
95.
95. Awesome. That's the starting of the metal. So it's 95. And where did it go? What is the final temperature of the metal?
30.
35. Awesome. This is the final of both of them, for both of them. Okay, so keeping that in mind. So it goes from 95 to 35, which means what's our delta T?
Change in 60.
60. Awesome. 60.0 degrees Celsius is our change. Absolute value equals, do we know the mass of the water?
100.
250 grams. Good. That's the mass of the water. Specific heat. Okay, it doesn't tell us what units we want, so we can use whatever we want. Let's use the 4.184 joules. 4.184 joules per gram degrees Celsius. If it told you what it wanted it in, then you could use whichever one was appropriate. And now let's do our temperature change of the water. Where does the water start inside of the calorimeter? What's
23.
the water temperature initially?
23 degrees.
23. Not 95. The water in the calorimeter is not 95. That was the piece of metal that went in here. And what is our temperature changing to?
35.
35. Awesome. So our temperature difference here is 12?
Yeah, 12.
12 degrees. 12.0 degrees Celsius. Okay. One step in your calculator, same as what we did before. I don't want you to algebraically change anything. What is C equal to? Don't forget, you start opposite your unknown, your x, and do what to those numbers? What do you do to the one opposite of x? You multiply, and then what do you do to these two? Divide, divide. Please enter that into your calculator and tell me what you get. 1.67. So we've got 3, 3, 4, 4, 3. So you want 3. So 1.67. Awesome. 1.67. What are the units? Well, our grams cancel out with our grams. Our Celsius cancels out with our Celsius. And what are you left with? Joules per gram degree Celsius. It's the same as the specific heat units on water. Good? There's no sign for C. They don't do positive, negative. Okay, so you just leave it at that.